Hi to everyone, my name is Nilo Redini, and today I'm going to present BootStomp on the security of bootloader in mobile devices. This work has been done by me and several of other my colleagues at UCSB in Santa Barbara. A little bit about myself. I am a fourth-year PhD student in computer security at UCSB in a SecLab group. My main interests include dynamic and static binary analysis, and you can find about me through my website or through my GitHub account or using my Twitter handle. Okay, so let's start. Let's start talking about bootloaders. So what is a bootloader? Shortly, a bootloader is a software module which initializes the device and its peripherals, loads the kernel from secondary storage, and jumps into it. On this work, we focused on Android bootloaders. Android bootloaders are very diverse. There is really no standard. Like, for example, ARM just gives some guidelines, but manufacturers are free to implement their bootloaders however they please. The booting process goes through several stages, as we will see soon. And bootloaders protect the integrity of user data and device. They provided what is called the trusted boot, as we will see soon. Also, modern bootloaders provide what is called the bootloader unlocking. Sorry. So, okay, one may ask, why attacking bootloaders? Well, an attacker controlling the bootloader process might boot custom Android OS, installing, for example, persistent rootkit, might in some cases, as we will see, break the device, and in some other cases can achieve control over peripherals. Overall, we identified 4 different properties that bootloaders should satisfy. First of all, the Android OS should be verifiable to be in a non-template state. A root process cannot interfere with peripheral setup. A root process cannot unlock the bootloader. And finally, a physical attacker should not be able to unlock the bootloader. Let's see the threat model that we use in this work. In this work, we assume that an attacker has control over the Android OS. In other words, she has root privileges. So one might ask, okay, cool, but if an attacker has root privileges, it's already game over, so why even bother? Well, the safety properties that I mentioned you read before should still hold anyway. In other words, a user should know if his device is in a template state. Here's a brief outline. I'm going to start talking about the booting process. Then I'm going to proceed with explaining what is the bootloader unlocking. I'm going to introduce you our tool, BootStomp. We're going to see an evaluation, some examples, and at the end, the conclusions. Let's start with the booting process. The booting process goes through several stages. In the first stage, happening what is called the God mode, which is called actually also the exception level 3 in ARM. In this mode, like processes has full control over the whole device. In this first stage, a very first bootloader, which is present in a ROM, is executed, and its purpose is to locate, to check for integrity, and to run a second bootloader called BL2 in the picture. This bootloader, in turn, will locate, check for integrity, and load a third bootloader called BL31. This bootloader will first set up the secure and not secure word on the processor, and it will then locate, check for integrity, and load the trusted OS, which will set up the peripherals and manage the trusted apps. BL31 also will locate, again, check for integrity, and load a fourth bootloader, BL33 in the picture, which will locate, check for integrity, and load the Android kernel, which, as we all know, manages all the Android apps. In this work, we focused on the BL33, which is the fourth and last bootloader, which is the only bootloader which actually interact with the Android unsecure operating system. Yeah. Sorry? Yeah, so this is how Google foresees the booting process. Okay, so as you can imagine, like each step in the booting process loads for the next step, checks for integrity, and then it jumps into it. This chain of check for integrity is called the chain of trust, and assure that when the phone is booted and running, the device is not in a template state. This chain of trust can be broken at the very last step when the BL33 loads the Android OS. And this is what is called unlocking the bootloader. I'm going to explain in the next slide what it is. So first of all, what is the bootloader unlocking? The bootloader unlocking is a means to skip the very last step of the chain of trust. So why one would like to do that? Well, the answer is that a user will want to do that in order to load some custom Android OS. And who should be able to do it? Only the device owner, which also has the physical access to the device. And this last step is actually enforced through through a two-step procedure. Let's see this procedure. First of all, the user has to unlock the phone, like using his PIN, his password, whatever. He has to set a precise option in the Android options called OEM unlocking. After that, she has to reboot the device and enter in what is called the fast boot mode and send some commands to finally unlock the bootloader. The first step of this procedure is thought in order to hinder attacker who might have the device, who can control the device. And this is why, because it's supposed that they don't know the PIN to unlock the phone. And the second part of this process is thought to be against root processes which might run on the phone. Okay, the unlocking state, also called device security state, is saved on persistent storage. This information should only be writable by high privileged components, for example, the bootloader or the secure OS. So the question that we posed to ourselves, that we wondered was, can a compromised Android OS affect the booting process? Well, the answer is yes. Let's see how. As I mentioned before, the bootloader reads from persistent storage. It locates the kernel, and it runs it. Let's assume now that the Android OS is somehow compromised. What might happen is that the compromised Android OS can write to persistent storage, writing some crafted data, compromising this data, which in turn will be read during the next booting of the phone. And in this case, if the bootloader contains some bugs, it can be compromised as well. Okay, another question that someone may ask is that, okay, but if the bootloader only loads the Android OS, how can an attacker harm the device, right? The answer is that bootloaders are very diverse. The booting process that I showed you before is just how Google suggests the booting process to happen, but in the wild, we found that only Qualcomm and NVIDIA follow closely the Google suggestions, and the BL33 runs in exception level 1. We found that Huawei bootloader is also responsible to initializing modem and peripherals, and what's even more worrying is that it runs in EL3, which is the mode which is called the God mode. So in theory, if an attacker has control over the Huawei bootloader, it can literally do everything on the device. Finally, MediaTek, we found that the MediaTek's bootloader is also responsible for initializing the modem, though it runs in EL1. Okay, so in order to understand whether an Android OS can actually interfere with the booting process, we need a tool to find this type of vulnerabilities. Bootloaders are hard to analyze. Why? Well, the source code is hardly available. We usually have to deal with binary blobs. Dynamic execution is impractical because the hardware is required to actually run the bootloader. And finally, as they execute before the Android OS, there is no known library or syscall. So usually, manufacturers write their own memcopy. There is no such memcopy function to look for. To overcome all of this problem, we wrote a static tool called BootStomp. BootStomp is an automatic static binary tool for finding security vulnerabilities in bootloader. It determines whether attacker-controlled data can influence the bootloader intended behavior, and it produces a traceable output. This is done so that a security analyst can actually verify the generated alerts and understand if an alert is a true or a false positive. BootStomp relies on a multi-tag Taint analysis engine, which is completely based on dynamic symbolic execution. And it uses this fully symbolic engine to trace attacker-controlled data. In this slide, you can see an overview of our system. First of all, the analyst has to somehow gather the binary blob, the bootloader. This can be done by extracting it from the device, if she has one, or getting from the internet. Once the binary blob is got, our system takes this as an input, and our system is mainly composed by two different parts. The first part relies on the tool IDA-Pro, and its purpose is to take the binary blob and find two different information, the seed of Taint and the sink of Taint. These two information are then passed on the second part of our tool, which is completely based on anger, and you use this information in order to analyze them and produce alerts. Okay, as I said, the BootStomp is a multi-tag Taint analysis engine. It's based on a multi-tag analysis engine. 4 quantities have to be defined. What are the seeds of Taint, the Taint propagation and removal policies, what are the sinks of Taint, and the Taint checking. Let's start with the seeds of Taint. We consider as seeds of Taint each data which is read from persistent storage and the data which is used by the unlocking procedures. BootStomp must find these functions automatically. Let's see how. So in order to do this, BootStomp relies on log messages. We actually found that log messages are quite common. And what BootStomp does is that it looks for specific keywords, like, for example, eMMC, or persistent storage, or kernel. Assume that it finds a known keyword, like in this case is eMMC. It tries to understand which function is responsible for this log string. In this case, it would understand the variable v23 is responsible for the string to be printed. And it would understand that v23 is actually an alias for v16, which in turn is returned by a function called sub700 BootStomp will consider this function as the function introduced in the Taint. Once these functions are identified, BootStomp should understand which one of these arguments is the buffer which will contain the data read from the secondary storage. In order to do this, we should understand which one of these arguments is an address, right? So in order to filter as false positives as possible, BootStomp tries to understand if any of these arguments is either a string or the value 0, as we assume that a valid pointer should be used. For all the arguments that we are not sure that BootStomp cannot understand the identity, it taints each one of them. Okay, the output produced by this very first step of our tool is presented in this picture. First of all, we get the method name, if it's present, which is the name of the function introduced in the Taint, the address of this very function, the caller name, which is the name, if present, of the function calling the seed function, the address of this last function, the Taint address, which is the address of the instruction having the call to the seed of Taint, the address of the basic block containing the call function, the number of arguments consumed by this function, and the list of arguments which can possibly be the buffer receiving the tainted data. And eventually, to information related to the log string that BootStomp used in order to infer that some function was a seed function. Optionally, an analyst can provide more seeds of Taint manually. This is done because we actually found that Bootloader Unlocking functions usually don't have log strings. Okay, let's talk about Taint propagation removal. Taints, in our work, are symbolic expressions encoding how the value is computed. Propagation and removal is implicitly done during the dynamic symbolic execution. Let's see how. So let's assume that we have some code. And in this case, we have that a seed function is called, and its value is assigned to a variable called ty. In a symbolic word, we create a new dynamic variable called, in this case, taintty, whose size we set to be equal to 1 page, so 4K bytes. This new variable is assigned to another variable called ty. Let's assume that later in the code, ty plus 5 gets assigned to a new variable called x. In this case, in the symbolic word, which will mean that a new variable called x gets the value taintty plus 5. And this is an example of how the taint is propagated. Finally, let's assume that somewhere in the code, the variable x gets some constant value 0x.beef. In this case, again, in the symbolic word, means that the symbolic variable x will get the value, the constant value 0x that beef. And this is how the taint is removed. Okay, let's talk about the sinks of taint. BootStomp aims to detect 4 different bugs: arbitrary memory writes, arbitrary memory reads, loops whose the user can control the number of iterations, possibly producing some denial of service, and finally, bypass unlocking mechanism, which means that we look for functions overwriting the device security state on persistent storage. In order to do this, we defined 4 different sinks of taint. We defined a sink of taint memcopy-like functions. As I said before, we can't really rely on function names because there are no really libraries. So BootStomp has to understand whether a function is a memcopy-like function. To do this, we use heuristics. First, we look for functions which have a loop where some data is copied from some source buffer to some destination buffer. And a memcopy-like function has to have many callers. We use a threshold for this. We consider as sink of taint the reference of a tainted variable. For example, let's assume that we have some tainted value, and the second field of this tainted value is assigned to some variable v. And this variable v, somewhere in the code gets the reference and used as function pointer. We consider this as a sink of taint. We also consider a sink of tainted variables which are used in loops conditions. For example, let's assume that we have this scenario where 2 tainted variables are used in the guard of a loop. In this case, the user could use them to run the loop as many times as she wants. And finally, we consider a sink of taint each write to persistent storage of a tainted variable, like in this example. Similarly to the seed of taint, the information produced by this step of BootStomp are in this picture, and they are the method name, which is the name of the sink of taint, the address of the sink of taint, the number of arguments that this function takes, and the possible arguments that the sink of taint can be present. Every time some tainted data reach some sink, an alert is raised. And along with it, a traceable output, as I mentioned before, is produced, which means that, as we will see at the end of this presentation, BootStomp produce each address for each basic block traversed from the beginning of the function to the sink of taint. Let's see the evaluation. BootStomp has been evaluated against 4 different bootloaders. We use Qualcomm LK. We use actually 2 different versions. The latest version that we found during this work, and an old one which was known to contain a bug. The NVIDIA bootloader, the Huawei bootloader, and the MediaTek bootloader. We had some problems in this stage analyzing MediaTek's bootloader because basically Anger was giving us problems. Overall, BootStomp raised 36 alerts, which 7 of them were found to be true positives, and 6 of them were found to be 0 days. So, okay, one question that one may ask is that, okay, you found bugs, but what can you do with them, right? Well, as I mentioned before, you can do a lot. For example, some bootloaders, as in the case of Huawei, they work in L3. So if you can exploit these bugs, you can actually take control of the device. We also ran an evaluation to find a locking bypass, and we found that 2 bootloaders, both the newest LK and an old version of LK and the Huawei bootloader, actually write the device security state on persistent storage. This doesn't mean that these bootloaders are vulnerable. It just means that the device security state is written on storage, on persistent storage. We actually checked, and we found that Qualcomm LK not to be vulnerable, but Huawei bootloaders to be. We'll see later, like the case. Okay, I'm going to show you now a very interesting vulnerability that we found of one of our bootloader. The bootloader in question is the Huawei bootloader, and the vulnerability was due to how the OEM information retrieval procedure was implemented. So, in Huawei, OEM info is represented by records. Records are stored on persistent storage, and each record has one or more blocks. Each blocks contain few information, like the information ID, the number of blocks composing the record, the current block number, data, and the length of the data. Each block is 4K bytes long, and the data field is 512 bytes long. Okay, let's see now the OEM info retrieval procedure. From a high point of view, this function takes three arguments: the info ID to look for, some buffer, and the size of this buffer. What this function does is that it retrieves the very first block from the record file. It iterates through each one of these blocks until it finds the block containing the wanted info ID. And then it just copies the data from these blocks to the provided buffer. And eventually, it returns just a flag. OK, let's see a couple of examples to understand how this function works. Let's assume that we have one record, which is composed by only one block. Let's assume that the info ID is set to 2. The number of blocks in the only block composing the record is 1, and the current block number is 1. Let's also assume that the meaningful data in the data field is composed by 128 bytes. And also, let's assume that a buffer pointed by some variable buff is as big as 200 bytes. What will happen is that, again, the function will start from the very first block on the record file. We'll iterate through each block containing the file until it finds the block containing the info ID equal to 2. And then it will check whether the size of the data containing the block is greater than the size of the provided buffer. If it is, the algorithm will stop. Otherwise, it will check if the current block number is less than the number of blocks composing the record. In this case, it is not. Therefore, the else branch is going to be hit. And in this case, the function, this procedure, will read len bytes from the block, and it will store them in the provided buffer. Let's assume now that we have a record composed by 2 blocks. So again, let's assume that the info ID is equal to 2. But in this case, the first block will contain, as number of blocks, the number 2, as current block, number 1, and 512 bytes of meaningful data. The second block, similarly, will contain the info ID equal to 2, the number of blocks equal to 2, but as current block, the number 2. And it will contain only 128 bytes of meaningful data. Let's see what happens. Oh, and let's assume also that the provided buffer to the function is as big as 712 bytes, which is enough to contain the whole data. Again, the function will retrieve the very first block containing the record file. It will scan each and every block until it finds the block containing the wanted info ID. It will check whether the buffer is big enough to contain the data, and as in this case it is, we'll check whether the current block number is less than the number of blocks. In this case, as it is, the if branch is going to be hit. And the function will read 512 bytes from the block and store them in the provided buffer. After this, the next block will be retrieved. The while will proceed with another iteration. But this time, the else branch is going to be hit, as this time, the current block is 2 and the number of block is 2. So in this case, 120 bytes are going to be read from the second block and store them in the provided buffer. So everything works fine and seems to be good. Let's consider again, though, the very first example where a record is composed by only one block. And let's assume now that an attacker has control over persistent storage. What she can do is that she can change each field in the blocks as she pleases. For example, in order to try to trigger a buffer overflow, she can change the data len block from 128 to some value 400, right? Let's see what happens. Well, there are not going to be any problems because the condition checking the actual buffer length is going to be satisfied, so actually the function will break and nothing will happen. Let's assume now, though, that an attacker modifies the field number of blocks. Instead of 1, as it was before, now she writes 2. In this case, again, the very first block is going to be retrieved. The wanted block is going to be found. This time, the check will pass as the block length is 128 and the buff length, the provided buff length is 200. But when the check about the current block number and the number of blocks is performed, this time we are going to hit the if branch. We're going to hit the if branch, and what happens is that 512 bytes are read from the block, and they are stored in a buffer whose size is 200. So in this case, we have a buffer overflow. We actually exploited this bug. We tried it, and we actually achieved control flow hijacking. This exploit can be found on our on the BootStomp repository, and we actually got a CV for it. Okay, let's talk about the unlocking bypass vulnerability that we found. Again, we found this bug on the Huawei bootloader, and the way that Huawei foresees the bootloader to be unlocking is the following. You have to go to the device website, you have to provide some number, and you get back what is called the OEM key. Later, you can use this OEM key and run some commands using the fast boots, and eventually the bootloader will be unlocked. This is like the function that is used by the Huawei bootloader to unlock the bootloader. The first step is that it reads some expected digest from the persistent storage. It then computes the hash of the provided OEM key by the user and store the value in some key digest. It then compares that if the two digests are the same. If so, some constant value is hashed, and the result is written on persistent storage. Now, even though an attacker might not know the OEM key, what she can do is that she can directly read from persistent storage and get the expected digest. After this, she just has to compute the hash function using the constant string with the expected digest and just write the result on persistent storage. By doing this, she will be able to unlock the bootloader by passing the OEM key part. Okay, let's see an example of BootStomp. So the very first step, as I said, takes place in IDA. I'm actually sorry, but I have some problems in IDA. I don't know why, and I can't see menus. I have some problem with GTK, so I'm just going to try to run it anyway. So the first thing, you have to run a script called find Taint, which, as I mentioned before, just scans the whole bootloader, look for log strings, and try to understand sinks and seed functions. The output produced looks something like this. Just have to copy it, which I already did, and store it in some file, which, let me check here. Huawei. Okay, which looks something like this. Once this is done, you have to write a very small configuration file. Oops. Okay, which contains information, among which the part of the info file that I just showed you, the part of the bootloader, and some other information like the number of bits of the architecture. Once you've done this, you just have to run BootStomp, the second part of BootStomp. Okay, like this. Now, this step is going to take between 20-25 minutes. So I actually ran this before the presentation and collected the results. The results, the results look something like this. So let's see a couple of them. In this case, we got 17 alerts. 5 of them were due to sinks, related alerts, which means that some tainted data reached some sinks. 8 of them were due to a loop where the user can control the number of iterations. And 4 of them were due to some dereferencing of tainted data. Let's see a couple of them. Okay. This very first one is actually the vulnerability that I showed you before, the one in the Huawei bootloader. So we have information. We have, for example, the address of the sink that has been reached. We have the reason why this alert has been raised. In this case, that we found that the sink accepts the parameter x2, which is the third parameter, which is tainted. We have the content of the parameter. And as you can see, it contains tainted data. We got the full path that led to the sink of taint. And we also report if during this path, the BootStomp found any completely taint conditions. I'll show you like in a minute. Okay, let's show this in IDA. So I renamed a few variables to the explanation. So the parameter which is found to be tainted, I call it tainted len, which is the third parameter of a memcopy-like function. In this case, if you follow all the blocks, you can actually do what I'm doing, just doing it by heart because I know this function. In this case, the taint len depends on some variable called v36. And v36 depends on some variable that I called, for simplicity, tainted data. Now, tainted data depends on a variable called v12 plus some offset. Okay, now if you do the math, like the point arithmetic, you will see that this variable is actually an alias for this guy, v22 plus 0x18. And as BootStomp identified this function as a seed of function by finding this log message, it will taint its argument. Actually, it will taint each one of them, but one argument which is found to be the value 0. As you can see, v14 is found to have the value 0. So it will taint each variable, each argument, but v14. So in this case, this value will be tainted, this variable will be tainted, which again is an alias for this guy, which will lead eventually to raise an alert because of this. Now, the completely tainted condition is this one, this guy. So BootStomp finds that all the variables used in this condition are actually tainted. So tainted data is the variable passed to the seed of function, so it's tainted. And this guy, v37, is actually an alias for the fifth field of tainted data. So both of them are tainted. Okay, let's see one last example about loop, Redini loops. Okay, let's see. Okay, in this case, BootStomp finds this variable to be tainted. Why? If we check, we see that this variable depends on this variable. This variable, it's an argument of a function pointer. If you proceed, you will see that this function pointer is an alias for this guy, which in turn is returned by a function which contains the keyword EMMC. So BootStomp will consider this function as a seed function. It will understand that here gets the reference and uses function pointer, and therefore it will taint each argument by the second, because again it contains the number 0. So it will taint in particular the third argument, which in turn will provoke this guy and this guy, as you can see, because this guy depends on tainted data, to be tainted. What does this mean? Well, this means two different things. First of all, if this is tainted, and this variable is just a counter which goes from 0 up to number of entries, an attacker can control the number of times this loop is iterated. Second of all, if an attacker can control this entry of the tainted data, it can actually achieve arbitrary memory reads, as you can see. No idea why I started from the beginning. Almost there. Okay. Okay. All the bugs were reported, acknowledged, and already fixed. And in conclusion, we proposed the first study to explore Android bootloaders. We provided an automatic technique to analyze bootloaders which produces traceable alerts. We found 60 days in various bootloaders, and we open sourced the tool that you can find with this URL. And I will take any questions.
Any questions? If you have any questions, you can raise your hands. Oh, come here.
Hi, morning.
Hi.
I understand you are using symbolic execution for making this automatic check of software. So, what is the limit basically in terms of number of lines of code or in terms of number of branches which can possibly be handled?
That explosion, right? So we provided a heuristic. For example, we only follow function calls which contain tainted data and up to a certain fixed call stack. This is one. We iterated through loops a fixed amount of time. We set this, I think, to 10, if I remember correctly. And we also use the timeout. So either all the paths get explored or the tool finishes when this timeout is triggered. What if you don't have? For what? For the bootloader? No, we use binaries. What? Okay.
Any more doubts? Wow. I guess we are done with the talks.